When nuclear fuel is no longer useful in power plants, yet it continues to emit radioactivity, it's considered radioactive waste. So long after the nuclear fuel can produce enough heat to be useful to be a power plant, it continues to emit this radioactivity. And because radioactivity can be extremely damaging to all living things, radioactive material or radioactive waste must be stored in these special containers under like really high secure locations. And so the use of nuclear fuels produces three kinds of radioactive waste: high level waste in the form of these fuel rods, low level waste, which is in the form of contaminated like clothing and tools and rags and other items that the maintenance people or plant operators use, and also the remaining uranium tailings, which are little pieces that are left over from when they tried to make it an actual sphere. And also like the residue left after uranium ore has been mined. The disposal of all three types of regulated by the government. But because it has the greatest potential to impact the environment, we're just going to focus on the high level radioactive waste. But it really doesn't matter what level we're talking about, whether it's the high level, the low level, or the tailings. Um, in each case, disposal must be handled with great care, and in each case, it's government regulated. Okay, so when it comes to this high level radioactive waste, after a period of time, these nuclear fuel rods become spent, meaning that they're no longer sufficiently radioactive enough to generate electricity efficiently. So each radioactive isotope has a specific half life, which is the time it takes for one half of its radioactive isotope to basically decay. And uranium 235 has a half life. Are you ready for this? 704 million years. So that means from today, 704 million years, a sample of uranium 235 will only have half as much radioactive material as it did today. And then in another 704 million years, it will lose another half of its radioactivity. So it will be one fourth as radioactive as it is today, the millions and millions and millions of years ago. I mean, in the future. Now, before we go further, radiation can be measured in a variety of units. A becquerel measures the rate at which a sample of radioactive material decays. It's a unit after Henry Becquerel. So one becquerel, is equal to the decay of one atom per second. That second unit is a Curie. That's another measure of radiation. It's 37 billion decays per second. So if a material has a radioactive level decay of 100 curies, then it has a half-life of 50 years. The radioactive level in 200 years would be 4 half-lives. And this is all math that we'll practice. So interesting enough, though, like Henry Becquerel, who came up with this unit, and then Curie, if you remember, there's also an element on the periodic table named after the Curies. Madame Curie is a real famous radioactive material scientist. And I even have a movie about her and her discoveries. But not only was she into radioactive material and such, but her husband was a physicist as well, and his name was Pierre. And even though the Curies have a element on the periodic table and a unit, an SI unit of measurement named after them, technically the prize went to Pierre, her husband. And Marie Curie, the wife, who actually was the brilliant one and popular one, didn't really get any credit. But if you open up a textbook these days, especially a chemistry textbook, it'll tell you that all this stuff was named after both of them. But we know that back in the late 1890s, when this was all discovered and happening, that was just not the case. She couldn't take credit, so Pierre had to. All right, anyway, fusion power. So we've seen that a nuclear fission occurs when the nuclei of radioactive atoms are broken apart into smaller, lighter nuclei. But nuclear fusion is the reaction that powers the sun and stars, and it occurs when lighter nuclei are forced together and produces heavier nuclei. And in this process, a great deal of heat is generated. The nuclear fusion reaction that is most promising for electricity generation is when two hydrogen isotopes fuse together and they make a helium atom. So as the reaction occurs, a small amount of mass is lost and an immense amount of energy is liberated and released. So nuclear fusion seems to promise a seemingly unlimited source of energy that requires only hydrogen as its input, and it produces a relatively small amount of radioactive waste. Unfortunately, creating fusion on Earth requires a reactor that will heat material to temperatures that are 10 times the core of the sun's temperature. So these temperatures make contamination extremely difficult. Containment extremely difficult. So far, the most promising technique has involved suspending a super hot material in a magnetic field, but the amount of energy required is greater than the energy output. So most experts believe that it will be several decades from now, or perhaps even longer than that, before the promise of nuclear fusion power can be realized and put into motion. All right, so in summary here of nuclear power and comparison with other fuels, currently our reliance on nuclear energy in the United States is subject to speculation and projections, but it is hard to know whether the positive aspects of nuclear energy will come to outweigh the risk of all the accidents and contaminations and radioactive waste. In 2006, applications for a new nuclear power plant in the U.S. were filed with the Nuclear Regulatory Commission for the first time in more than 2 decades. And in 2012, licenses were approved for these 2 nuclear power plants. It does appear that up to 5 nuclear power plants may be in the works right now in the United States. But basically, this table summarizes the major benefits and consequences in these conventional energies that we've discussed. So one thing that's not in my presentation here are nuclear accidents, because we're going to discuss them in class. But in March of 1979 was 3 Mile Island, and that's a power plant in Pennsylvania. And then, in addition to that, in April 26 of 1986 was the nuclear power plant disaster, Chernobyl, in the Ukraine. That's another one that we're going to discuss. And I'm probably going to pick up a third one here, and that'll be Fukushima, which happened March 11th of 2011, if my memory serves me correctly. And that was due to a earthquake. And so we're going to talk about those 3 accidents in particular because those are the ones that tend to show up on exams and questions. So stay tuned.